In the infinite darkness of space, far beyond the warm embrace of sunlight, where our star shrinks to nothing more than a fierce bright point among billions of others, there reigns a colossus, a world so vast, so ancient, so brutally indifferent to everything we know that it defies every attempt at comprehension, the largest planet in our solar system, the oldest guardian of the void, the most savage, relentless, and magnificent force in all the planetary neighborhood we call home. Jupiter. Say that name slowly. Let it settle. Because this is not a planet you visit. This is not a destination you dream of one day standing on. This is a place where the laws of nature operate at extremes that would reduce any human being, or any machine we have ever built, to atoms in a matter of hours. A place where storms larger than entire continents have raged without pause for hundreds of years, where lightning bolts crackle with energies 1,000 times greater than anything Earth's atmosphere can produce, where the very concept of a surface is an illusion, a gradual transition from choking clouds to crushing liquid to something even more alien than either. For centuries, Jupiter was nothing more than a mysterious smear of light. The ancient Babylonians tracked its movement across the sky 4,000 years ago, weaving it into their myths. Galileo Galilei turned his primitive telescope toward it in 1610 and discovered 4 moons orbiting it. The first proof that not everything in the cosmos revolves around Earth. That discovery was one of the most dangerous ideas a human being had ever produced. And for a long, long time, that was all we had. A bright dot, 4 tiny moons, a handful of cloud bands visible through increasingly powerful telescopes, a giant question mark hanging in the outer solar system. But human curiosity does not accept question marks for long. And so, eventually, we decided to do something that many thought was impossible. Something that pushed the limits of engineering, physics, mathematics, and human endurance to their absolute breaking point. We decided not merely to fly past Jupiter, not to peek at it from a safe distance. We decided to become its companion, to enter its domain, to sit in orbit around this monster for years and peel back its secrets one by one. This is the story of that mission, a story of catastrophe and salvation, of broken dreams and stubborn genius, of machines that refuse to die and engineers who refuse to quit. A story about what it takes to reach the most hostile environment our solar system has to offer, and what we found when we got there. This is the story of Galileo, an odyssey that became a legend. Space is our future. In the 1970s, humanity made its first tentative grasp at Jupiter. The Pioneer 10 and Pioneer 11 spacecraft, brave little machines, primitive by any modern standard, made the initial journey, returning blurry images and critical data about the radiation environment waiting in the Jovian system. They were scouts, pathfinders, and what they found was sobering. Jupiter was not just big, it was radiating, it was violent. It was, in ways that had not been fully anticipated, deeply hostile to any technology we might send near it. Then came the Voyagers. Voyager 1 and Voyager 2 remain among the most celebrated spacecraft ever launched. In 1979, they performed their legendary flybys of Jupiter, and what they sent back transformed our understanding of the solar system overnight. Boiling cloud systems the size of planets. The Great Red Spot, a storm that had been raging since before the American Revolution, revealed in stunning, swirling detail. The 4 great Galilean moons photographed up close for the first time. Volcanic Io, ice-covered Europa, cratered Ganymede, scarred Callisto, and, perhaps most shockingly, volcanic eruptions on Io, the first active volcanoes ever detected beyond Earth. The images were breathtaking. They appeared on the front pages of newspapers around the world. They ignited a generation of scientists, engineers, and dreamers. They asked more questions than they answered. But there was one fundamental problem with the Voyager missions, and scientists knew it even as they celebrated. It was merely a glimpse. The Voyagers came screaming through the Jovian system at tens of thousands of kilometers per hour. They had hours, not days, not weeks, in which to observe. They were tourists, not residents. They snapped photographs the way a traveler leans out the window of an express train, grabbing impressions of a landscape that blurs past in seconds. The images were extraordinary, but the data was thin. The questions multiplied faster than the answers. What lay beneath those cloud layers? What was the atmosphere actually made of, layer by layer, from the top of the clouds to the crushing depths? Was there truly a liquid ocean beneath the ice of Europa? And if so, was anything alive in it? What was the internal structure of Jupiter itself? How did its immense magnetic field work? Where did all that energy come from? The scientists were left standing in their laboratories, surrounded by thousands of new questions and an almost unbearable hunger for more. And so, in the late 1970s, NASA made a decision that would define the next quarter century of planetary exploration. They would build a spacecraft worthy of Jupiter, not a flyby probe, not a tourist, a dedicated orbiter, a machine that would enter the Jovian system and stay, that would circle Jupiter for years, not hours, that would study its atmosphere, its magnetosphere, its radiation belts, and its strange and fascinating moons with the patience and precision of a scientist who has nowhere else to be. They would name it Galileo, in honor of the man who first pointed a telescope at Jupiter's moons and changed the world. And it would be the most naively ambitious, brilliantly engineered, catastrophically troubled, ultimately triumphant spacecraft in the history of human space exploration. The engineers and scientists who designed Galileo faced a challenge that had no clean precedent. Jupiter was not simply far away. It was actively hostile to technology. The planet generates the most intense magnetic field of any object in the solar system save the Sun itself. That field traps charged particles, electrons and protons, and accelerates them to relativistic speeds, creating radiation belts that surround the planet like invisible rings of death. Any spacecraft that entered those belts without heavy shielding would be fried within hours. Its electronics would fail, its sensors would go blind, its computers would crash. Then there was the question of what to do once you got there. A simple orbiter circling Jupiter and photographing its clouds would have been valuable but incomplete. The real prize, the thing that would justify the cost and the risk, was a direct probe into the atmosphere itself, not a remote observation from orbit, an actual descent, a machine that would fall into the clouds of Jupiter and transmit data back as it plunged deeper and deeper into conditions of increasing pressure, increasing temperature, and total, annihilating darkness. No one had ever done anything like this before. No one had ever sent a probe into the atmosphere of a gas giant. The engineering challenges were not merely difficult. They were, in several respects, completely new. There was no manual to consult. There was no precedent to follow. The team that built Galileo was among the most talented collection of scientists and engineers NASA had ever assembled. They were brilliant. They were creative. They were perhaps slightly mad in the way that all people must be who attempt the genuinely impossible. And they came up with a design so clever, so audacious, so beautifully complex that it stands even today as one of the great achievements of human engineering. Galileo would be a dual-spin spacecraft. That is to say, it would be two spacecraft in one. The rear section of the vehicle would spin continuously, 3 times per minute, providing gyroscopic stability to the entire craft during its long journey through deep space. This was not new technology. Spin stabilization had been used on spacecraft before, but Galileo went further. The forward section of the spacecraft, the part that carried the cameras, the spectrometers, the imaging instruments, would remain fixed, despun, pointing steadily at its target while the back half rotated around it. 2 spacecraft mechanically coupled, rotating in opposite senses relative to each other. No one had ever built this kind of hybrid before. The mechanical and electrical interfaces required to connect a spinning section to a non-spinning section to transmit power and data across that perpetual rotation were nightmarishly complex. Engineers spent years working out the problems, but it worked. On paper, it worked brilliantly. And then there was the probe. Attached to the main spacecraft like a medieval knight's shield, the atmospheric probe was a titanium sphere encased in a carbon phenolic heat shield of staggering thickness. It weighed 340 kilograms. It was packed with 6 scientific instruments, a mass spectrometer to analyze the chemical composition of the atmosphere, a helium abundance detector, a net flux radiometer to measure energy transport, an atmospheric structure instrument to record temperature and pressure, a lightning and radio emissions detector, and a nephelometer to study cloud particles. The plan was simple in concept and staggering in execution. As Galileo approached Jupiter, the probe would be released, ejected from the main spacecraft like a spear thrown at the planet. Months later, moving independently, guided only by the laws of orbital mechanics and the gravity of Jupiter, it would enter the atmosphere at a precisely calculated angle. Too steep, and it would burn up before the parachute could deploy. Too shallow, and it would skip off the atmosphere like a stone off water, vanishing into deep space. The entry angle had to be right. The entry speed would be 170,000 kilometers per hour, the fastest atmospheric entry in the history of spaceflight. The friction of the upper atmosphere would heat the shield to 15,000 degrees Celsius. That is approximately 2.5 times the temperature of the surface of the sun. Not some distant, abstract comparison. 2.5 times hotter than the sun's visible surface. The heat shield would ablate. It would burn away, layer by layer, sacrificing itself to protect the instruments within. Half the shield's mass would be gone within minutes. But if the engineers had done their calculations correctly, if the titanium sphere within would survive, the parachute would deploy, the probe would descend. And for approximately 58 minutes, before the crushing pressure finally destroyed it, the probe would transmit its findings back to the main spacecraft overhead, which would relay them to Earth. This was the plan. This was the audacity. This was Galileo. The project was approved, funding was allocated, teams across multiple NASA centers and international partner institutions began the work of turning this breathtaking vision into metal and silicon and wire. They had no idea what was coming. The original launch plan was elegant. Galileo would lift off in May 1986 aboard the space shuttle, tucked inside the cargo bay, along with a powerful upper stage rocket called the Centaur G'. The Centaur was fueled by liquid hydrogen and liquid oxygen, the most energetic chemical propellants available. It would ignite in low Earth orbit and hurl Galileo on a direct trajectory to Jupiter. 2.5 years of cold, quiet transit through the outer solar system, clean, fast, safe. Then the 28th of January, 1986 happened. 73 seconds after liftoff, the Space Shuttle Challenger disintegrated over the Atlantic Ocean. 7 astronauts died. Among them was Krista McAuliffe, a schoolteacher from New Hampshire, selected to teach lessons from orbit. Thousands of schoolchildren across America were watching live when the orbiter broke apart. The nation went into shock. The investigation revealed a culture within NASA in which known risks were systematically downplayed and schedule pressure overrode engineering judgment. Reforms were sweeping and painful. And among the decisions made in the aftermath was this: no more liquid-fueled upper stages in the shuttle cargo bay. A crewed vehicle and a tank of liquid hydrogen was deemed an unacceptable risk. The Centaur G' was canceled. For Galileo, this was not merely a setback. This was potentially catastrophic. The Centaur was not just convenient, it was physically necessary. The spacecraft was too heavy, and Jupiter too far away to reach the outer planet on any reasonable trajectory without that powerful kick. Without the Centaur, there was no mission. Galileo sat in a storage facility. Months passed, then a year, then more. The spacecraft that had been designed for cold, distant Jupiter was sitting in a temperature-controlled warehouse in California, being periodically loaded onto trucks and shuttled between laboratories as components were inspected, tested, and reevaluated. Each truck journey subjected the delicately assembled machine to vibrations, not violent vibrations, gentle ones, the kind you would not notice if you were sitting in the cab, but repeated, cumulative, insidious. No one knew yet what those vibrations were doing. Finally, the engineers found a solution. A less powerful but acceptable upper stage, the inertial upper stage, running on solid propellant, not liquid, could work, but only if Galileo took a radically different path to Jupiter. Instead of a direct trajectory, the spacecraft would take what is called a VVEJGA route, Venus-Venus-Earth-Jupiter Gravity Assist. It would swing past Venus once, then loop back past Earth twice, using each planet's gravity like a slingshot to gradually build up speed. A baroque, intricate, almost absurdly complicated journey that would take not 2.5 years but 6. On October 18, 1989, Space Shuttle Atlantis climbed into the Florida sky. In its cargo bay sat Galileo, gleaming and patient, its golden-colored thermal blankets catching the morning light. 5 astronauts carried it to orbit. The payload bay doors opened. The spacecraft was ejected into the void on powerful springs, tumbling slowly away from the orbiter. The upper stage fired. Galileo was on its way, but not the way anyone had planned. The new trajectory sent it first toward Venus. Venus, the inner solar system, the hot zone, the place where sunlight is twice as intense as at Earth's orbit. Galileo had been designed for cold. Its thermal management systems were built around the assumption that it would spend almost its entire operational life in the dim, frigid outer solar system. But now it was heading inward, toward the sun, carrying with it the most critical and fragile component of the entire mission, the high-gain antenna. This antenna, a golden umbrella-like dish nearly 5 meters in diameter, was Galileo's voice. It was the instrument through which the spacecraft would eventually send back the thousands of images and gigabytes of scientific data that justified every dollar spent and every risk taken. Without it, Galileo was mute. The backup antenna, a small, low-gain device tucked against the spacecraft's body, could transmit data, but at a rate so pathetically slow that the mission would be crippled. The problem was heat. If the high-gain antenna were deployed, open like an umbrella, during the spacecraft's passage through the inner solar system, the sun's radiation would pour into it and destroy the delicate metallic mesh. The antenna had to remain folded, closed, stored, like a furled umbrella in a raincoat pocket, until Galileo was safely in the outer solar system where the sunlight was gentle enough to allow deployment. This was the plan, and the team was confident it would work. But they had overlooked something small, something catastrophic in its smallness. April 1991, Galileo was now in the asteroid belt, safely beyond Mars, retreating from the sun at last. The team in Pasadena at NASA's Jet Propulsion Laboratory sent the command, deploy the high-gain antenna. The motors activated, the antenna's ribs began to unfold, and then they stopped. 3 of the 18 ribs that made up the antenna's structure were stuck. Not merely stiff, fused, locked in place by what engineers would later determine was the failure of a dry lubricant on the rib guide pins. The lubricant had been worn away during those years of truck journeys between laboratories after Challenger. In the vacuum of space, without lubrication, the metal surfaces had cold welded, a phenomenon where clean metal surfaces in a vacuum bond to each other at the atomic level. The ribs were not just stuck. They were part of each other. Instead of a gleaming parabolic dish 5 meters wide, Galileo had deployed a crumpled, asymmetrical tangle of metal spokes. The mission, $1.5 billion, 15 years of work, the careers of hundreds of scientists and engineers, the dreams of a generation of planetary scientists had just gone partially blind. The team spent months trying to free the antenna. They rotated the spacecraft rapidly, trying to shake the ribs loose. They pointed it at the sun to heat the metal, then rotated it into shadow to cool it, cycling the temperature to expand and contract the stuck components. They fired thrusters. They commanded the antenna motors to run at maximum power. Nothing worked. The ribs remained bonded. There was no mechanic to send. There was no repair mission possible. Galileo was now hundreds of millions of kilometers away, on its own, carrying a broken antenna and a cargo of irreplaceable scientific instruments, and no way to send their findings home at any meaningful rate. The backup low-gain antenna could transmit at a maximum of 16 bits per second. To put that in perspective, a single uncompressed photograph of Jupiter would have taken roughly a month to transmit at that rate. There were thousands of photographs planned. There were hours of atmospheric probe data. There was data from 6 different instruments on the probe alone, plus 12 instruments on the main spacecraft, plus years of orbital observations. At 16 bits per second. The mathematics were brutal. The mission, as designed, was impossible with the resources now available. And this is where the story shifts, because what happened next was not surrender. It was not recalculation and reduced expectations and a dignified acceptance of partial failure. What happened next was one of the most remarkable examples of human problem-solving in the entire history of space exploration. The team at JPL did not have the option of fixing the hardware, so they decided to fix the software instead, entirely, remotely. While the spacecraft was hundreds of millions of kilometers away, using radio signals that took up to 52 minutes to travel one way from Earth to Galileo and back. They would reprogram the spacecraft's brain. Galileo's onboard computers were, by 1991, already antique. They had been designed in the late 1970s and built in the early 1980s. By the time the reprogramming effort began, personal computers were advancing at astonishing speed, but Galileo was still running on processors with a fraction of the capability of a modern pocket calculator. Working with these primitive machines, the software team at JPL embarked on a multi-year effort to develop new data compression algorithms, new ways of encoding the scientific data so that less bandwidth was required to transmit each piece of information. They essentially taught a computer from the 1970s to compress files. They invented, for this specific purpose, a custom image compression format that worked somewhat like what we now know as JPEG compression, identifying redundant information in images and throwing it away without losing the essential scientific content. They wrote routines that would allow Galileo to record images and data to its onboard tape recorder, compress them, strip out the black emptiness of space surrounding Jupiter and its moons, all those pixels of pure black that contain no information, and transmit only the meaningful content. This reprogramming effort took years. It required writing entirely new flight software, testing it exhaustively in simulators on Earth, then transmitting it to the spacecraft in packets, knowing that any error, any corruption, any undetected bug might render the spacecraft inoperable 400 million miles from the nearest human being. It worked. Out of the original 50,000 photographs and scientific measurements planned for the mission, Galileo would ultimately return approximately 14,000 images and an enormous quantity of scientific data, less than planned, but still more than enough to revolutionize our understanding of the Jovian system. Every single piece of it squeezed through an antenna the size of a trash can lid. At the data rate of a very slow 1990s modem, Galileo had been crippled, but it had been saved, and it arrived at Jupiter with impeccable timing. Because something extraordinary was happening in the Jovian system. In March 1993, amateur astronomer Carolyn and Eugene Shoemaker and David Levy were scanning the sky with a modest telescope on Palomar Mountain when they noticed something strange. A comet, but not a normal comet. It appeared not as a single point of light with a tail, but as a fragmented chain, a string of pearls strung across the sky. It was later determined that this comet, Shoemaker-Levy 9, had passed too close to Jupiter on a previous orbit, perhaps decades earlier, and the tidal forces of the giant planet's gravity had torn it apart. The fragments, 21 of them, ranging in size from a few hundred meters to perhaps 2 kilometers across, were now arrayed in a line stretching hundreds of thousands of kilometers, and they were all aimed directly at Jupiter. Calculations confirmed the inevitable. Between July 16th and July 22nd, 1994, these 21 fragments would strike Jupiter in sequence, the first deliberate prediction of an impact between solar system bodies ever made. For the first time in recorded human history, we would be able to watch a cosmic collision in real time. The entire astronomical community mobilized. Telescopes around the world were pointed at Jupiter. The Hubble Space Telescope, recently repaired after its famous mirror defect was corrected, was pressed into service. Observatories in Europe, Asia, and the Americas all coordinated their schedules. This was a once-in-a-lifetime event, possibly a once-in-a-civilization event. The last time something like this had happened, there were no human beings on Earth to watch. But there was a complication. The impacts would occur on the far side of Jupiter, the night side, the hemisphere facing away from Earth. The explosions themselves would not be visible from Earth. Telescopes would only see the aftermath, the enormous dark scars left in the cloud tops as each fragment struck, rotating into view as the planet turned. except one observer was in exactly the right position, traveling at precisely the right angle on its long gravity-assist trajectory toward Jupiter. Galileo, broken, battered, half-blind Galileo, had a perfect view of the impact zone. For these few extraordinary days in July 1994, Galileo was the only instrument in the solar system positioned to observe the impacts directly. It watched. Through its tiny backup antenna, at its agonizingly slow transmission rate, it sent back images and data. The scientists who received those transmissions sat in hushed rooms and stared at their screens. The largest fragments struck with energies measured in the millions of megatons. Fragment G, one of the biggest, produced an explosion that released more energy than all the nuclear weapons on Earth combined. The fireball it generated rose 3,000 kilometers above the cloud tops. The dark bruise it left in Jupiter's atmosphere was larger than the entire planet Earth. The mark lingered for months. The lesson was not lost on anyone watching. Jupiter is not simply a planet. It is a gravitational vacuum cleaner, a world whose immense mass sweeps the inner solar system of comets and asteroids that might otherwise strike Earth. Without Jupiter, our planet would be hit far more frequently. The evolution of complex life on Earth may be partly a story about having the right giant planet in the right place. But Jupiter can also be a catapult, deflecting objects toward the inner solar system rather than away from it. The solar system is a shooting gallery, and Jupiter is both the greatest shield and the greatest gun. Galileo watched the shooting gallery in action, and then it flew on. December 7th, 1995, the day of arrival. 6 years, 15 billion kilometers, gravity assists from Venus, twice from Earth, an asteroid flyby of Gaspra in 1991 and another of Ida in 1993, discoveries yielding the first confirmed asteroid moon, a tiny object named Dactyl orbiting Ida. 2 years of struggling with a broken antenna, one software revolution performed remotely in deep space, and now, at last, Jupiter. 5 months before arrival, the main spacecraft had separated the atmospheric probe, releasing it on its collision course with the planet, allowing it to coast independently through the void on a trajectory that would intersect Jupiter's atmosphere at precisely the right angle. The probe had no propulsion of its own after separation. It could not correct its course. It was committed. It would go exactly where orbital mechanics sent it. December 7th, 1995. The probe arrived first. It hit Jupiter's upper atmosphere at 170,000 kilometers per hour. For scale, a bullet fired from a rifle travels at roughly 3,000 kilometers per hour. The probe was 56 times faster. The deceleration was catastrophic, up to 228 times the force of Earth's gravity. Any human being aboard would have been instantly liquefied. The titanium sphere inside the heat shield experienced forces that no human engineering had ever before been asked to withstand. The heat shield worked, reaching temperatures of 15,000 degrees Celsius, hotter than the surface of the sun. The outer layers of the shield ablated away, boiling into superheated plasma that streaked behind the descending probe like a comet's tail. Half the shield's mass was vaporized in less than 2 minutes, but the instruments within survived. At approximately 50 kilometers above the cloud tops, the parachute deployed. The plunge became a descent. The scientific instruments switched on, and the probe began to transmit. What it found was not what scientists expected. The probe descended into one of Jupiter's hotspots, areas where the upper atmosphere is unusually clear, allowing relatively deep observation. In one sense, this was unfortunate. These hotspots are atypical regions, and the data from them does not represent the average Jovian atmosphere. But in another sense, the scientific findings were still extraordinary. The winds at the probe's entry point were ferocious, up to 700 kilometers per hour, blowing not from the equator toward the poles as prevailing atmospheric models had predicted, but in constant powerful jets perpendicular to Jupiter's rotation. These winds were not driven by solar heating. At Jupiter's distance, the sun provides only 3% as much energy per square meter as it does at Earth. The energy driving Jupiter's weather comes from within, from the residual heat of the planet's formation, still slowly radiating outward after 4 billion years. Lightning flashed around the descending probe, bolts 1,000 times more powerful than any on Earth, radio emissions crackling through the static of the alien atmosphere. The The probe measured the abundance of helium in the atmosphere, slightly less than expected. It detected water, but again, less than expected. Jupiter was drier than the models had predicted. Whether this was because the hotspot was anomalously dry, or because Jupiter itself was drier than models suggested, became a scientific debate that would last years. Deeper. The probe descended deeper. The sunlight that had already been reduced to a dim orange glow as the probe passed through the upper cloud layers faded further, then was gone entirely. Total darkness. The instruments continued to transmit. Temperature rising, pressure rising, wind screaming around the outer casing of the probe. The temperature rose to 153 degrees Celsius. The atmospheric pressure reached 23 times that of Earth's sea level. And then, at 58 minutes into the descent, at roughly the 22 bar pressure level, approximately 130 kilometers below the cloud tops, the signal stopped. The probe had been crushed, dissolved into the endless depths of Jupiter's atmosphere, its atoms joining the 4-billion-year-old chemical soup that is the interior of the solar system's largest planet. It would fall for perhaps many hours more, the pressure increasing as it dropped, the temperature climbing, until even its titanium structure finally melted and dispersed. In its 58 minutes of life in Jupiter's atmosphere, the Galileo probe transmitted 3.5 hours of data, recording continuously and transmitting at high speed to the main spacecraft overhead. It was a sacrifice. It was always intended to be a sacrifice. And like any meaningful sacrifice, it gave us more than its cost. But the mission was only beginning. While the probe was dying in Jupiter's depths, the main Galileo spacecraft had reached the planet and performed its orbit insertion burn, a 49-minute firing of its main engine that slowed the vehicle enough to be captured by Jupiter's gravity. It was the single most critical maneuver of the entire mission. If the engine had failed to fire, or had fired for the wrong duration, Galileo would have continued past Jupiter into deep space, never to return. The maneuver worked perfectly. Galileo was now in orbit around Jupiter, and what followed was 2 years of increasingly astonishing discovery, followed by another 6 years of extended mission operations as NASA kept finding reasons to keep the spacecraft alive and working, even as its electronics deteriorated, its memory faulted, and its aging systems needed ever more creative management from the team in Pasadena. The first moon to be scrutinized closely was Io, the innermost of the 4 Galilean satellites. Nothing in the solar system had prepared scientists for what Galileo found there. Io is a hell world, not metaphorically, not as a poetic description, literally. The first and most immediate observation, the one that leapt off the images as soon as they were assembled, was volcanic eruption. Not one volcanic eruption, not a handful. Io was erupting everywhere. Volcanic plumes towered 500 kilometers above its surface, fountaining sulfur and sulfur dioxide into the near vacuum of space. The surface was not ancient and cratered like most solid moons. It was smooth, fresh, constantly renewed. Every square kilometer of Io was being resurfaced every few million years. Impact craters were being buried as fast as they could form. The energy source for all this activity was Jupiter itself. The same titanic gravity that had torn apart Shoemaker-Levy 9 was relentlessly kneading Io's interior. As Io orbited Jupiter, pulled gravitationally not only by the giant planet, but by its orbital resonance with the neighboring moon Europa, the moon was constantly being flexed and stretched. This tidal heating, the conversion of orbital and gravitational energy into internal heat, was pumping enormous quantities of energy into Io's interior, melting rock and driving constant volcanic activity at a rate far exceeding anything on Earth. Io was a solar system curiosity, a moon more volcanically active than any planet, a world of fire orbiting a world of storms, an object so geologically extreme that every textbook about the outer solar system had to be rewritten after Galileo's observations were processed. But the real revelation, the discovery that would echo through the decades that followed, and that continues to drive the most exciting missions in planetary science today, came at the next moon. Europa. Europa is, at first glance, a striking object. It is slightly smaller than Earth's moon. Its surface is not cratered and ancient like most solid bodies in the solar system. It is smooth and pale, crisscrossed by a network of brown and reddish lines that resemble, to the human eye, the cracked surface of a hard-boiled egg. It has very few impact craters, which means its surface is geologically young, constantly being renewed by some process that erases the scars left by ancient impacts. What process? As Galileo made its close flybys of Europa, coming within 200 kilometers of the surface on several passes, its magnetometer instruments detected something extraordinary. The magnetic field around Europa was not a simple interaction between the Moon and Jupiter's powerful magnetosphere. There was a secondary magnetic field, an induced field, that changed as Jupiter's magnetosphere rotated, and the only mechanism that could produce such an induced field was the presence of a conducting fluid beneath Europa's surface, a fluid being moved and stirred by the changing external magnetic field. There was only one fluid candidate that made geochemical sense: salt water. Beneath Europa's icy crust, estimated to be tens of kilometers thick, Galileo's magnetometers were detecting the signature of a global ocean of liquid, salty water, not a lake, not a localized reservoir, a planet-wide ocean covering the entire globe under the ice, with more liquid water in it than in all of Earth's oceans combined. And water, as every biologist will tell you, is the essential ingredient of life as we know it. Wherever liquid water exists on Earth, in the deepest ocean trenches, in scalding hydrothermal vents on the seafloor, in brine pockets deep in Antarctic ice, life exists. Life that needs no sunlight, life that derives its energy from chemistry and heat, life that has found ways to survive in conditions that would kill any ordinary organism. If similar life existed in Europa's ocean, if the principles that drive life in Earth's extreme environments were operating beneath those kilometers of ice, then we were not alone in the solar system. This was not science fiction. This was the conclusion of hard physics and data from a spacecraft in orbit around Jupiter. Life in Europa's ocean was not proven, but it was, for the first time in human history, a scientifically credible possibility, not wishful thinking, a hypothesis supported by data. The discovery changed everything. It redirected the future of astrobiology and launched a research program that continues to this day. By 2000, Galileo had been in Jupiter orbit for 5 years. It had survived the crushing radiation environment. Barely. The intense particle bombardment had degraded its electronics, causing computer resets, data corruption events, and instrument failures. Engineers worked around each failure with software patches, operational workarounds, and determination. But even before Galileo arrived at Jupiter, there had been a second near catastrophe. The tape recorder, that antique magnetic storage device on which the entire data system depended, nearly failed just weeks before the probe entry in late 1995. The tape jammed. For 15 hours, the spacecraft was in crisis as the tape wound and rewound, the risk of it snapping growing with every pass. The engineering team, hundreds of millions of kilometers away, determined that the final section of tape had become friction welded to the mechanism. They made a brutal decision: abandon the last 25 meters permanently. Never use them. Sacrifice that storage space rather than risk losing everything. The tape survived, and on those remaining meters was some of the most important data ever collected in planetary science: the temperature profiles, wind measurements, lightning readings, and atmospheric composition from 58 minutes inside Jupiter's clouds. If that tape had snapped in October 1995, we would never have known what lay inside the solar system's largest planet. By 2003, Galileo had been in orbit for nearly 8 years. It had made 35 orbits of Jupiter. It had completed flybys of all 4 Galilean moons. It had survived things that should have killed it many times over, but its fuel was running out. The hydrazine propellant used for attitude control and orbital adjustments was approaching exhaustion. When it ran out completely, Galileo would lose the ability to point itself, to maintain its orientation, to operate its instruments in any controlled way. It would become a ghost ship, still broadcasting, still receiving signals, but tumbling uncontrolled through the Jovian system, guided only by gravity and random chance. And a tumbling uncontrolled spacecraft, guided by random chance in the Jovian system, might eventually crash into something. Specifically, it might crash into Europa. This was not an abstract concern. Galileo had not been sterilized before launch. The sterilization standards applied to the Galileo spacecraft were lower than those applied to missions specifically designed to land on bodies considered potential habitats for life. Because at the time of Galileo's construction, there was no compelling reason to believe Europa's ocean existed. The ocean was discovered by Galileo itself during the mission, which meant that Galileo was carrying Earth microbes. Not many, not obviously, but microbes are extraordinarily resilient, and some of the bacteria capable of surviving in vacuum, in radiation, and in the deep cold of space are precisely the kinds of organisms that might, if introduced to Europa's ocean, be capable of surviving and reproducing. To allow Galileo to crash uncontrolled into Europa would be to risk contaminating the one place in the solar system, outside of Earth, that might harbor indigenous life. It would be the most catastrophic act of biological pollution in history, not because we would certainly kill anything living in Europa's ocean, but because we would never be able to tell the difference afterward. We would never know if the life we found there came from Europa or from a warehouse in Pasadena. The decision was made without significant debate. It was the only ethical choice available. On September 21, 2003, NASA sent Galileo its final command. The spacecraft's remaining propellant was used in a precisely calculated burn that altered its trajectory, not toward Europa, not toward any of the other moons, toward Jupiter itself. At approximately 50 kilometers per second, 180,000 kilometers per hour, Galileo hit Jupiter's upper atmosphere. The spacecraft that had traveled more than 4 billion kilometers, that had survived 6 years of interplanetary transit and 8 years of orbital radiation torture, that had been reprogrammed in deep space and resuscitated from the edge of mission failure, not once but several times, that had revealed the volcanic fury of Io and the hidden ocean of Europa and the violence of the largest comet impact in recorded history. That spacecraft vanished. No signal, no transmission, no record of its final moments. Within seconds, the friction of Jupiter's upper atmosphere would have stripped away the thermal blankets, the solar panels, the structural members. Within minutes, the entire spacecraft would have been dissolved into the bottomless chemical ocean below. Its atoms, aluminum, titanium, silicon, copper, carbon, dispersed into the body of the planet it had spent 8 years studying. Galileo became Jupiter. What Galileo left behind is not merely a catalog of scientific results, though the catalog is extraordinary. It is a story about what human beings are capable of when they refuse to accept defeat. When a spacecraft's primary communication system fails irreparably, you rebuild the software. When the tape recorder jams, you abandon what you cannot save and work with what remains. When the original mission design becomes impossible, you find another way. Longer, more dangerous, more creative, and you go anyway. Galileo made possible the future of outer solar system exploration. It turned the question of life beyond Earth from speculation into hard science. Europa Clipper launched in October 2024 and en route to the Jovian system for a 2030 arrival carries 17 science instruments dedicated entirely to the follow-up question that Galileo first asked: could Europa's ocean support life? The spacecraft is gone. Its atoms are part of Jupiter, but the questions it asked are still being pursued by scientists who grew up watching its images emerge from the darkness at 16 bits per second, pixel by patient pixel. The most dangerous mission to Jupiter ever, the mission that went wrong in almost every possible way, the mission that succeeded anyway. We will go back. We are already going back, and perhaps one day a lander will touch down on Europa's ice, and a drill will descend, and something extraordinary will come up from below. We will owe that moment, whatever it holds, to Galileo, to the machine that died so that an alien ocean could remain unpolluted, to the engineers who refused to give up, to the spacecraft that became the planet it loved. I hope you enjoyed the video. If you did, please hit the like button. It genuinely helps this channel reach more people who love space and science. Subscribe if you haven't already, and hit that notification bell so you don't miss what's coming next, because we've got a lot more of the universe left to explore together. See you out there.